Hello, I'm Abhra Choudhury from the University of Exeter, presenting cross-modal fusion distillation for fine-grained sketch-based image retrieval. This is a joint work between myself, Massimiliano Mancini, Yanbei Chen, Zene Pakata, and Anjan Dotto. Here's the outline of my talk. Let's start with the problem definition. Sketch-based image retrieval, or SBIR for short, is the task of retrieving photos from a gallery given a query sketch. Coarse-grained SBIR returns all photos that belong to the same class of the query sketch. In contrast, fine-grained or FGSBIR requires identifying a specific photo that has the closest match to the query sketch. The latter is the problem that we address in this work. How can we formulate this as a learning problem? FGSBIR datasets typically have instance-level correspondences with multiple sketches corresponding to a single photo. We can thus pose this as a metric learning problem where matching photo sketch pairs are mapped close to each other in a metric space, whereas non-matching pairs are mapped farther apart. Our methodology is inspired by the following novel observation. Contrary to the widespread belief, we posit that certain modality-specific features might actually be useful for retrieval. Consider this example. Contrasting shades in a photo may be depicted by a sketcher via a sparse collection of zigzag lines. Both denote the same underlying concept of contrast and hence is useful for instance matching, but manifest differently in different modalities, thereby being modality specific. Thus, instead of prematurely discarding such features, we perform a modality fusion to retain them in the representation space. We then transfer this knowledge to independent encoders, which can leverage the richness of the fused representation space without having to perform the expensive cross-attention operation at test time. We call our end-to-end model cross-modal VIT. We leverage the ability of vision transformers to perform patch-wise operations. Given the patch embeddings from the photo and sketch modalities, we perform a modality fusion across the set of patches from the two modalities via our cross-modal attention or XMA operator as follows. We swap the class embeddings between the two modalities and propagate them through a learnable transformation that would project them to the representation space of the opposite modality. We perform an attention operation between this transformed class embedding and the patch embeddings of the other modality. Finally, we add the output from the attention and the transformed class embedding and project it back to the representation space of the original modality. We iterate this process k times, k being equal to 12 in our implementation, and the final output vector could then function as a modality fused representation. It is on this fused representation space that we perform contrastive learning, which allows us to preserve modality-specific instance discriminative features. Inspired by the Q-based versions of InfoNC, we design the cross-attention Q contrast or XAQC loss. We maintain a queue of fused sketch representations from previous mini-batches, which act as negatives for the InfoNC-based contrastive loss. The positive is the fused photo representation from the XMA operator. We call this part of our model the teacher. Although powerful, the XMA operation is much more computationally expensive for similarity-based search as compared to the dot product, which is the standard operation for this purpose. To leverage the rich representations learned via XMA, we perform cross-modal knowledge distillation of the fused representations into independent encoders, which play the role of students. Our knowledge distillation phase consists of two components, contrastive and relational. In the contrastive component, we use the XAQC loss to contrastively match the representations of the teacher and the student for the same input. And we do this separately for the individual modalities. In the relational component, we maintain geometric invariants like distances and angles between the representation spaces of the teacher and the student. We perform experiments on both single and multi-class FGSBIR datasets. We use QMAL SHU-V2 and CHAIR-V2 for single class evaluation, and results show that our method surpasses existing state-of-the-art in most cases while having no extra computational overhead. For multi-class evaluation, we use the Sketchy dataset, which is a large-scale FGSBIR dataset with 125 classes. We have been able to surpass the average human level performance on Sketchy as well as all existing state-of-the-art without requiring any form of extra information like textual annotations. To verify the stability of our model across backbone choices, we vary the backbone sizes of the teacher-student pair. We see that the performance remains quite stable across different backbones, with larger teachers generally being more effective than larger students. We also see that the convergence times of students are much lower when the teacher's backbone is larger. Regarding the size of the queue in the XAQC loss, we see that the performance levels off after a certain point, and there's no merit to increasing it beyond that point. From the qualitative retrieval results, we can see that if the target photo has a significant number of discriminative local features compared to others in the gallery, it always appears in the top one. However, correct instances that get demoted in rank are preceded by ones that bear significant resemblance to the fine-grained local features of the queue. Here are a few attention maps obtained using our cross-modal VIT model. And here we depict examples where modality-specific features uniquely identify an instance. Sketchers use techniques like scribbles to illustrate color or texture differences, for instance in the shoe, and grid or mesh-like structures or primitive shapes like squares or triangles as approximations for complex wrap patterns, as in the chair and the turtle's shell. Consider the example in row 1. While a large variety of shoes would have the same kind of front, which modality shared models focus on, our model, by the virtue of modality fusion, is capable of attending to more discriminative features like contrasting color or texture depicted by scribbles, or a partition denoted by a line, while also capturing shared features like local geometry. UMAP visualizations of the representation space show that our model is able to properly align the photo and sketch modalities while being instance discriminative. To conclude, we proposed retaining modality-specific instance discriminative features for FGS-PIR and designed a cross-attention based modality fusion operator for achieving the same. We used knowledge distillation as a way to leverage the richness of fused representations while avoiding test time computational overhead. Finally, we achieved state-of-the-art performance on both single-class and multi-class benchmark FGS-PIR datasets. Here are the links to our paper and implementation. Please get in touch with me at this email address if you have any questions, comments, or suggestions. Thank you for your attention.